Thanks for inviting me to give a talk here. I will turn off my video and just share my screen. The PDF of the slides have been shared in the chat. Is that right?
Yes, that's right.
Yes.
Okay. Yeah. So just to warn you, if in case my internet goes off, continue looking at the slides. I'll be right back in a minute or two. Okay, so I'll get started. So that's the topic of my talk. This was a paper which I recently put up on arXiv, which is joint work with Chris Woodward. So I start out with some preliminaries to introduce the problem. So I start out with telling you what a symplectic cut is. So let X be a symplectic manifold and consider a separating hypersurface Z. And we assume that there is a circle action in a neighborhood separating hypersurface, which is a Hamiltonian circle action. So what a symplectic cut does is it cuts off the manifold along the hypersurface Z, and so we get two manifolds with boundary, and we mod out those boundaries by the S1 action. So the effect is we get two symplectic manifolds, X plus and X minus, and Z mod S1 is a symplectic divisor in both these manifolds. So yeah, so both X plus and X minus contains Z mod S1 as a relative divisor. And a point blow up of a manifold. So if you take any point and take a Darboux chart around it, and mod out the S2 n minus 1 by the S1 action, one side of it would be the blow up and the other side would be CPN. Now let's move on to the notion of a multiple cut, which is a natural generalization of the single cut. So in this case, we have a symplectic manifold and a collection of hypersurfaces with S1 actions on their neighborhoods. And at the intersection of these hypersurfaces, the S1 actions fit together into a Hamiltonian torus action. So this is a picture to keep in mind. So Z1, Z2, and Z3 are hypersurfaces which meet in Z0, and all of these neighborhoods have S1 actions. And in the center where all of them meet, there is torus action, so that this S1 actions are the restrictions of the torus action. And when we execute the multiple cut, what we get is three different symplectic manifolds. So the hypersurfaces, when they are modded out by S1, we get divisors, and the intersection region is modded out by the T2 action, and that would be the intersection of the divisors. So these divisors are normal crossing divisors, and their intersection is also obtained as modding out a certain submanifold by a torus action. So yeah, so the output is a collection of symplectic manifolds called cut spaces with relative normal crossing divisors. So in our example, for X1, Z1 mod S1 are relative divisors whose intersection is Z0 mod T2. Okay, so the question we are ask ourselves today is, if we apply a multiple cut to a symplectic manifold, can counts of holomorphic curves in the unbroken manifold be expressed in terms of counts of holomorphic curves in the broken manifold? The ideal case would be if we can somehow say that the mod space of curves in the unbroken manifold is the basis of curves in the broken manifold. But that is only partially realized. Okay, so there are three objects of interest today. So unbroken maps, these are holomorphic maps in X. broken maps, these are broken maps, these are maps in the cut spaces satisfying some matching conditions, which we'll get to. And the third is split maps, which is a version of broken maps with the matching condition weakened. And that's the third one is what will help us get towards the dream with the product of moduli spaces, which I talked about in the previous slide. Okay, so yeah, so in the rest of the talk, in the first part of the talk, I'll talk about how to go from unbroken to broken. And after that, we talk about how to go from broken maps to split maps. Okay, so I start with the case of a single cut when going from unbroken to broken. And this is familiar territory because this is basically SFT, but I review it nevertheless. So basically we want to say that holomorphic curves in this manifold X somehow correspond to some holomorphic curves in the cut manifold. So the way to arrive at a homotopy equivalence is by stretching the neck. So by neck, I mean the neighborhood of the separating hypersurface. So what we do is we submanifold with a family of almost complex structures in which the neck, which have necks of length mu, and we let mu go to infinity. So by what I mean is when I say a neck of length mu, it means that the neck region is a fibration over y. I remind you that y is the relative divisor, and the fibers are cylinders of length nu. Okay, and here we are just varying the almost complex structure. We are not doing anything else. So therefore, the moduli spaces of J nu holomorphic curves are homotopy equivalent for all nu. And we get to broken maps when we take the limit nu going to infinity. And this has been well studied by Hofer and collaborators and Ionel and Parker. And this is the compactness side of the result, which says that if you have a sequence of holomorphic maps with bounded area in a sequence of neck stretched manifolds, then a subsequence converges to a broken map. Which is, right, and as we all know, in SFT, we get components of the map lying not only in these pieces x plus and x minus, which were the cut spaces, but also there will be map components stuck in a neck. So the target space of a broken map is a broken manifold. So it consists of the cut spaces, x plus and x minus, and then it consists of a long neck, which is z times r compactified. And by the compactification, I mean that at infinity, I add in the divisors to make the compactified space a symplectic manifold. So it is the compactification of z mod r by adding divisors at plus and minus infinity. So the resulting space is a P1 bundle over the relative divisor. And this compactified space is called a neck piece because it was obtained by stretching the neck. So a broken map has components in x plus, x minus, and the neck piece that satisfy a matching condition at nodes. And what's this matching condition? So the matching condition says that if you have two components which share a node, then the lift of the node maps to the same point on the relative divisor. So this point and this point are the same points on the relative divisor y. And secondly, remember that Y is a divisor, so there are isolated intersections with holomorphic curves, and the intersection multiplicity is equal on both sides. And let's see why we get this kind of a structure in broken maps. And the main picture I want you to keep in mind from this section is that these nodes arise as a result of the convergence of long cylinders in the neck region. So these are long cylinders with small area. So essentially, we should also view these two sides of the node as arising out of the cylinder. So since it's the same cylinder, it's going to map to the same point on the relative divisor and have the same intersection multiplicity. So intersection multiplicity is just how many times it kind of goes around Y. And yeah, this is another useful picture, which is that if you look at a converging subsequence from mu close to infinity, the maps look like this. So they are small packets of area separated by long cylinders with small area. And these cylinders eventually become nodes. So they basically wrap around the divisor an integer number of times. Right, and yeah, and the components in the next region, they converge in the target space. So that modulo or translation in the target space. For example, in this picture, e to the t phi nu e nu converges to a limit component of the broken map. So going forward, there is idea of another structure which is going to come into play in the multiple cut situation, which is that you would have noticed that unlike the picture in Hofer, I am not keeping track of the numbered sequence of buildings, of floors in a building. I've just like said all my components in the next piece just map to the next piece, but instead the kind of data I would like to remember is the relative position of the map in the neck region. So if you look at the translations for any component, so recall that in the previous slide we saw this. For example, the fifth component has these translations. So if you were to divide the translation by the length of the total length of the neck and take limit going to infinity, then for every curve component, you get a number between 0 and 1, and that gives an embedding of the graph underlying the map into a line segment. So, and that's the tropical graph in the case of a single cut. Okay, so with these kind of ideas from the single cut, we move forward to the multi-cut picture.
Can I ask a brief question?
Sure.
The pictures that you're drawing, they seem to be genus 0.
Yes.
Are the statements that you're making also about higher genus?
I expect them to go through, but in the paper, we only prove the genus 0 case.
Okay, I understand. Thank you.
Didn't do it because we were dealing with this.
Thanks.
Okay, so okay, thanks. Multiple cut. So for for the datum of a multiple cut comes with a polytopic decomposition of the Euclidean plane Rn. So this is an example. So this was the first example which we considered earlier, if you remember. So the polytopic decomposition for that has 3 top dimensional polytopes, P1, P2, and P3. And the set of polytopes is closed under intersection. So we have a bunch of smaller dimensional polytopes thrown in. Okay, but the running example that I'd like you to have in mind is that of two symplectic cuts, two orthogonal single cuts. So when you put two cuts together, it's a multiple cut with this this polytopal decomposition. So there are 4 top dimensional polytopes and their intersections. And then there is this point where all of them intersect. And yeah, so the cut spaces look like this. These smaller dimensional polytopes, they correspond to relative divisors of cut spaces. Okay, so just like we did neck stretching for a single cut, the same thing can be done for a multiple cut. And in our example, we have considered of two cuts. It's particularly easy to see what's going on. So there is this horizontal band which is stretched to a thickness of nu, and similarly this vertical band is stretched into nu. So you get this small square in the middle gradually becomes a larger and larger square. Right, and also I want you to notice that the gray regions have an action, have an S1 action, and the white region has a T2 action. Okay, and one of the theorems we prove in this paper, generalization of the result, the compactness and gluing results for a single cut. I just state the compactness result here, which is that if we have a sequence of maps in neck stretched, multiply neck stretched manifolds, Ionel and Brett Parker, and the idea that the broken map in multiple cut situation has an underlying tropical graph, and that is being a important combinatorial invariant. That was first realized by Brett Parker. And okay, so the situation, so the convergence picture which we drew in the single cut case, we can draw a very similar picture for the case of a multiple cut. There are these small pockets of energy separated by long cylinders. And I'm carrying over the color scheme. So the dark gray is the cut spaces, and the gray is the stretched version of the divisors, and the white is the intersection of those divisors. Okay. So now the question is, what is the kind of space, what is the kind of object the sequence converges to? We call it a broken map. So I'll spend some time describing what a broken map is. So the target space of a broken map is a broken manifold. So earlier we saw a cut space, and a broken manifold is basically it's obtained by thickening the divisors, the relative divisors cut space. So let me be more specific. So recall that XP1, XP2, XP3, and XP4 are just cut spaces. And those were separated by divisors. So in a broken manifold, instead of those divisors, you have a P1 bundle over the divisor. So this is exactly like the neck piece in the single cut. So, so for example, for XP34, you have a P1 bundle sitting on top of it. So that's like the neck piece separating XP3 and XP4. So if you were to just focus on the bottom row, that's exactly what goes on in case of, that's exactly the broken manifold for a single cut, which we are more familiar with. But when we put it all together, the point in the picture, gets stretched in two directions, and it becomes a P1 square bundle. So that's where our maps are going to live. And as I introduce the space, let me also say what are the symmetry groups that act on these pieces. So on the P1 bundles, there is a C star action. And on the P1 square bundle, there's a C star square action. And on the original cut spaces, there is no action of any group. Okay. 1 minute. So another relevant piece and object for describing a broken map is a dual complex. So in a dual complex, we have a polytope corresponding to every polytope in the polytopal description, but of complementary dimension. So for example, in the original polytopal decomposition, P1 was top dimensional, but in the dual polytope, P1, the dual of P1 is just a point. And P12 was a co-dimensional, it's dimension 1, and so on. So why is this relevant? Because in addition to the data of the holomorphic maps, it also has information of tropical graph. So earlier we saw that the tropical graph was just in a line set, and since now there are two cuts, it's now embedded into two line segments, which is a square. But the general version is to be thought of as a dual complex. So yeah, so the dual complex consists of a complementary dimensional polytope, P dual, for each polytope P in the polytopal decomposition. Okay, finally I come to the definition of a broken map. So a broken map consists of a domain nodal curve C, which is modeled on a graph. And on each component, there's a holomorphic, rather pseudo-holomorphic map into one of the components of broken manifold. And these maps satisfy certain matching conditions at nodal points, which I'll describe in the very soon. And additionally, a broken map also has the information of a tropical graph. So we saw what roughly a tropical graph looks like in a single dimensional case. And we, for example. So just I want to emphasize that a tropical graph is a combinatorial invariant associated to a broken map. So, so the moduli space will have different pieces corresponding to different tropical graphs. So it's not continuous invariant. Right, so for example, we considered a sequence of maps which look like this. And that sequence will, the sequence converges to a broken map whose tropical graph is of this form. So that can be, basically it can be read off from the translation sequences used in the translations of the target space for which these maps converge. So this shape of the map just gives us the shape of the tropical graph. Any questions?
Yeah, I had a quick question at some point when you said embedded graph. Why are we supposed to think of it as being embedded?
As opposed to immersed, you mean?
Yeah, yes.
I just, it's not, yeah, I think it's the wrong use of the word. I shouldn't have said that. It's my mistake.
So it's like there's an abstract graph, and then there is this tropical thing, and then there's a map, tropical map from the graph.
I meant, yeah, exactly. Instead of an abstract graph, it's a graph sitting in a space. So I didn't mean in terms of an embedding of a manifold.
Okay.
So
okay.
Yeah, I'm not saying they won't intersect. Yeah, it just sits in that space. Yeah.
Okay.
And Sushmita, while you're taking questions, this is Nate Bottman. So Is there any non-standard analysis when you're considering these degenerations, or is it all fairly standard, maybe SFT style analysis?
So interestingly, the proofs for the compactness, the McDuff-Solomon style proofs literally go through. I didn't need anything new. So except for, if you know how the domain, you know what the limit domain is, the target is can be computed in a very straightforward way. And the reason why that happens is that our maps are stable maps because we are using a divisor to stabilize the domains. So yeah, so if on that front, that's pretty easy. And the gluing, I mean, there are some, you know, you have to be more careful with the gluing here.
Okay, thanks.
Okay. Right, okay. So getting back to the matching condition at the nodal points. Okay, so how are nodes formed? So as we saw earlier, so these long cylinders become nodes in the limit broken map. So a node WE in a broken map is formed by the convergence of long cylinders lying in a region with action of some complex torus, depending on where the edge lies. So yeah, different edges are going to have different toruses acting on them. So in our example, yeah, if you look at this example, the long cylinder that's formed, that would have the action of C star square. So now, yeah, so the cylinder converges to a node which has integer intersection multiplicities with divisors. So let's take that intersection multiplicity vector and consider the complex one-dimensional torus generated by the intersection multiplicity vector, and that sits inside this torus which acts where the cylinders lie. Yeah, so these longs, because much area in them, they are just as in the single cut case, they are asymptotically close to these orbits of the torus generated by the intersection multiplicity. And then the matching condition can be written down as follows. We just mod out the neighborhood of the node by T mu C. And then the evaluation on both sides is the same on the quotient of the space. So if you just think about it, what this translates to in the single cut case, T mu C is always the same cylinder in the single cut case. So, and this space over here, this is essentially the relative divisor for the single cut. So here, the one thing that is different is you don't automatically have a space on which you check for matching, but you need to mod out by the right torus in order to get the space where you can do the matching. Yeah, and one more remark here is it's that the matching condition has dimension x minus 2, unlike ordinary holomorphic curves where the codimension is just dimension x. So therefore, the presence of a node does not decrease the index of the map. So there is another way of looking at the matching condition, which has been adopted by Yonel. There, what you do is we say that, so there is 3 different conditions there. The first is that when you quotient it by the full torus, this is not just the one-dimensional torus, when you quotient it by the full torus and map it, in this case, just to this point object, then the evaluation is same on both sides. And the intersection multiplicities with both the divisors are the same on both sides. And then there is a third condition which says that you do a Taylor expansion, the leading order terms have the same coefficient on both sides. Okay, and the intersection multiplicity is related to the slope. So if you have this a picture in mind, this picture in mind, we see that these cylinders just become the edges in the tropical graph. So what I was just going to say is that, yeah, that if E is an edge connecting two components, U plus and U minus, in the tropical graph, the slope of E is equal to the intersection multiplicity mu1 comma mu2. So mu1 and mu2 are the intersection multiplicities with these two relative divisors. Okay. So so that so that basically finishes the definition of a broken map. So let me recall. So a broken map has components in different pieces of a broken manifold. So I described the broken manifold, and then we talked about what the matching condition is. And in addition, there is a tropical graph which satisfies this condition, that intersection multiplicities as nodes corresponds to the slopes of edges. Okay, so that's a broken map. And now the next thing I'm going to talk about is what are the symmetries of a broken map. So we saw earlier, let me go back to that slide. Yes, we saw here that different pieces in a broken manifold have a torus of different dimensions acting on them. So when we have a broken map, we are going to have these torus actions on different pieces. But now the question is, will they preserve the matching condition at nodes? So the tropical symmetry group is the subgroup that preserves the that preserves the matching conditions at nodes. So basically it is the subgroup which takes a broken map to a broken map. And it is given by an obvious condition, which I would say, don't worry about this because the picture is going to be more meaningful. And the picture is this, that you can read off the tropical symmetry group from the tropical graph. So in particular, the really nice part of this tropical symmetry group is that if you can move the vertices in the tropical graph without changing the edge slopes, then every degree of freedom corresponds to a generator of the tropical symmetry group. So for example, in the left picture, there is no way you can move these vertices without changing the slope of the edges. Whereas in the right picture, these two vertices can be moved to the vertices indicated with dots. So there is a one-dimensional freedom there, which means that the tropical symmetry group is C star. So that generates symmetry group. And if we look at the single cut case, the entire tropical graph lies on a line segment, which means that except for the endpoints, if there is anything lying in the middle of the line segment, it can just be moved. And so therefore, the only rigid tropical graph is one with no neck pieces. So yeah, I mean that aligns with our experience, which says that, you know, if you have a neck piece, there's a C star action on the neck piece, and that's not going to change anything about, you know, it's not going to it's not going to break anything, unlike in the multiple cut case where we do have to worry about the matching condition at nodes. So the C star action in the neck piece in case of a single cut does not affect the matching condition at nodes. Okay, so coming to the specific case, so in the paper, our results are about Lagrangian Floer theory. So we consider a Lagrangian submanifold, which is located away from the separating hypersurfaces. And after the multiple cut, the Lagrangian is in one of the cut spaces in the complement of the relative divisors. So, and the theorem we obtain as a result is that the moduli spaces of, so if we restrict to any area bound, the moduli, so I only consider zero-dimensional moduli spaces. So the index zero, the index zero disks in an unbroken manifold are bijective to index zero broken disks. So that's the theorem. Yeah, and sorry.
So just to make sure I understand the content of that theorem, like you're saying that not only is there a bijection between these two zero-dimensional moduli, but it's a bijection which also just respects the filtration on both. The area filtration.
Yes, the area is the same, right? So if we have a sequence in a certain homology class in X, and we look at this, the sequence converging, and we get a limit in the a limit broken map, it's going to have the same area as the maps in the sequence, right?
Great, thank you.
Okay. Okay, and why are rigid tropical graphs interesting? It's because we are primarily interested in index zero maps, and if a broken map has index less than equal to 1 only if the underlying tropical graph is rigid. Otherwise, the orbit of the tropical symmetry group is at least 2-dimensional. So therefore, when we are counting these rigid maps, we are looking at maps which are modeled on rigid tropical graphs. So in particular, the moduli space partitions, and the partition is indexed by rigid tropical graphs. Okay, and by using counts of these broken disks, one can define the composition maps of infinity algebra called the broken Fukaya algebra, and we show that the ordinary Fukaya algebra is homotopy equivalent to the broken version. So that basically just falls out of this bijection result that we proved earlier. Okay, so in the rest of the talk, I'm going to talk about the second agenda that we had of going from broken maps to split maps. So this of degenerating the matching conditions on nodes. So let me, before I talk about what we do in this paper, I'll review some of the older stuff which has been done for the case of a single cut. So we recall that in a single cut, the matching condition just says that the node on both sides maps to the same point on Y, which is the relative divisor. So because of this matching condition, the moduli space of maps, which looks like this, the moduli space of maps as in the figure, is a fiber product of this form, where the map to Y is the evaluation map at the node on both sides. So, so using deformation by Morse flow one can show that the fiber product is homotopic to a product. And I outline how the proof goes. So the way to do it is we consider a variation of broken maps where the matching condition of a node is replaced by a deformed matching condition. Namely, this is the deformed matching condition. So instead of saying u plus and u minus map to the same point at the node, they map to a point which differs by a time t flow of a Morse function. So phi yt is the time t gradient flow of a Morse function on y. So counting these kinds of, so this is called a t-deformed map, and one can show that the moduli space of t-deformed maps is homotopy equivalent to the moduli space of broken maps. That feels very natural because one can think of broken maps as zero deformed maps, and you can go continuously from 0 to t. And the next step is to take the limit as t goes to infinity. So then the Morse trajectory becomes a one of infinite length, that is, it acquires a breaking at a critical point. And then with a little more work, one can show that the moduli space of broken maps is homotopy equivalent to the moduli space of infinite deformed maps. So these are infinite deformed maps. So where the lifts of the nodal points are connected by a broken Morse flow line. So the flow line breaks at a critical point T, and as a result, the moduli space of infinite deformed maps can be written as a sum of products. So both these objects on either side of the node can be counted independently of each other because there is no longer a matching condition. There is just, all you have to keep track of is which is this critical point P in question, and those can just be counted. Okay, so
I have another question.
Yeah.
When you say that these are homotopy equivalent, I'm a little bit confused why that would be the case. Because I would expect more that they are cobordant, that somehow.
Yeah, so the A infinity algebras are homotopy.
Okay, so the actual moduli spaces are cobordant, and then the counts are homotopic by the, okay, thank you.
Yeah.
Wait, so I have possibly a more naive question. Is there some index assumption that says that there's a unique gradient flow as you've depicted? Like, instead of literally being a product, shouldn't there be some moduli of flows?
Do you mean multiple breaking? Yeah. So, yeah. Do you mean twice broken flow lines? Something.
Oh, like I'm just wondering if there's an index assumption between like the nodal point and the critical point P. Like, you know, even with an index assumption, it looks like
there is. You mean an index assumption on the index of P?
Yes, like the Morse trajectories, like even with an index zero assumption, there could be multiple such Morse
you
flows.
should see that one of them is an incoming one and another is outgoing. So the index of P doesn't matter. It's going to cancel on both sides.
And is the nodal point not a critical point?
Do you mean before the deformation?
Right, the function capital H, you're just ensuring that the nodal point of the curve is not a critical point?
No, I'm not assuming anything like that.
So then there could be...
So is your question that will there be a critical point? There will be a critical point because we are talking about an infinitely long flow line, right?
No, but I think I understand. So you're just saying like the nodal point, like where that red curve intersects your divisor, like it is not a critical point of capital H, and that's why there's no moduli of flows to P. I think I understand. I think.
Okay. Okay, maybe we can talk more about it at the end.
That sounds great. Thank you.
Okay. Okay, so why are multiple cuts different? So what goes wrong in multiple cuts is that even in most examples, you would, the reasonable most, I mean, the most functions which are going to give you good results, if you take some of those most functions, then the stable or unstable submanifolds will coincide with relative divisors. So you end up with pictures like this, where this W minus will have to lie on a relative divisor, and which means that when you do the convergence, for what I mean by do the convergence, so here you take a sequence of T deformed maps with T going to infinity. So you're doing a convergence there. So when you do a similar kind of convergence, you will get bubbling, and you won't get a reasonable Morse trajectory anymore, because when you hit a relative divisor, you move into a different space and form a bubble. So the earlier approach completely fails in case of a multiple cut. So generically, there are additional bubbles in the limit as the deformation parameter goes to infinity. So we do something which looks quite different. And we do it in a slightly restrictive case, where I assume that the edges lie on toric varieties whose torus invariant divisors are relative divisors. So pardon me if this looks technical, but it's going to be simplified in the next slide. So the main example to have in mind is that one of the cut pieces is a toric variety, all whose torus invariant divisors are relative divisors, and the Lagrangian is a torus orbit. So, and what we will do is we will deform the nodes that lie on disk components, namely nodes which look like this. So one of the ends of the node lies on a disk. So that's basically to ensure that the disk part of it lies inside the toric variety. So we only deform those nodes which lie on the bounded divisors of a toric variety. Anyway, so, but this is a nice, easy example to have in mind for the rest of the talk. So let's just take X to be a toric variety and apply a multiple cut on it. And what's the multiple cut? We take neighborhoods of torus invariant divisors and separate them using cuts. So the polytopic decomposition is as in this figure. So there is one big space called XP0, which is symplectomorphic. Sorry. Oh no, I didn't, this is wrong. I meant to say diffeomorphic. This isn't, that's a typo. So XP0 is diffeomorphic to X, but with a smaller symplectic form. And the torus invariant divisors are relative divisors, as you can see. Okay, so this is a good example to keep in mind. And the Lagrangian, of course, is a torus orbit here. Okay, so now basically I will talk about deforming nodes which lie here. So if I have a disk here and a sphere here or a sphere there, those are the nodes I'm going to deform. So, and what that means is that suppose the edge is free to move here. So on either side, it hits an intersection with, it hits a normal crossing. It's not an ordinary point. The critical points are going to be very special points. So so that's why the situation is very different from what we saw in a single cut. So recall that the matching condition is of this form, where we mod out the neighborhoods of nodes by a one-dimensional torus, and then we compare the evaluations at the nodal points. So now the first step is similar to what we did earlier for the single cut case, is that we consider a deformed map. So a deformed version of the matching can be written as follows. So basically the matching condition in this top line is replaced by a matching condition which has this multiplicative factor, and this multiplicative factor is an element in a torus. Okay, and then we let this parameter, this deformation parameter, go to infinity and look at what happens in the limit. So we will prove that the sequence converges to what's called a split map. So this new object that we will obtain will not have any matching conditions on nodes. But so which means that we are gaining some dimension. But what also happens on the side is that this this object acquires some extra tropical symmetry, and in particular, the codimension of the matching condition is equal to the dimension of the tropical symmetry group. So it's so I'll do an example right after this. I'm just setting this up and telling you what to expect. So and another thing to keep in mind is that when you do this deformation, there is a choice we are making. So the moduli space of split maps has a new parameter, namely the direction in which the deformation parameters approach infinity. So that's part of the data of the split map. And so what we saw is that if we start out with index 0 broken maps and and deform it to obtain index 0 deformed maps, in the limit, we obtain a split map of much larger index, and it also has a symmetry group, which is equal to its index. So the right result to state, I mean, just to get the statement right so that the indices add up at least, the result should look like this. In that, again, the homotopy equivalence is it's actually an infinity homotopy equivalence. So this is not quite an accurate statement. So but I think that to give the idea, this is good enough. So what I mean to say is that the moduli space of broken maps is homotopy equivalent to the moduli space of split maps modded out by the tropical symmetry group. So a single map here becomes an entire orbit on the split side. I repeat, a single map in the broken side becomes an entire orbit on the split side. And using, yeah.
Sorry, minor question. So what kind of space is the space on the left-hand side? Is it a manifold? And also, is this about all dimensional components? Like you talked about the algebra, which I think only sees the zero dimensional and one dimensional.
Yes, so we are only talking about 0 and 1 dimensional. The analysis is only for 0 and 1 dimensional.
I see. And in the one dimensional case, sorry, go ahead.
Yeah, so this M here would be either the dimension of the tropical symmetry group or +1.
I see. And is there some like geometric result expected for higher dimensional moduli?
There is problems with the perturbation technique we are using with stabilizing divisors, so that doesn't work for higher dimensions. So we are using this. Yeah, and there might be other problems also which I have not gotten into.
Thank you very much.
Okay, so using these split disks, using counts of split disks, we define an A-infinity algebra called the tropical Fukaya algebra. Counts of, defined by counts of symmetry orbits of split disks. And finally, okay, so this homotopy equivalence is an honest one. So this is a homotopy equivalence of A-infinity algebras between the tropical Fukaya algebra and the broken Fukaya algebra, which in turn is same as the ordinary Fukaya algebra of X. So all of them are homotopy equivalent. Okay, now comes the example. So let's start with the simplest disk of Maslow index 2 in this broken manifold. So this consists of a Maslow index disk, or Maslow index 2 disk U plus and a sphere U minus. And here the matching condition is just that the evaluation on this divisor is the same. And it's good to keep track of the tropical graph. So each of these vertices, sorry, each of the curve components has a vertex here, and that's the edge is a straight line over there. So this is P0, this is P0 dual, that's P1, so that's P1 dual. Okay, so we deform it in the direction, in the right direction. So tau is pointing right. So U plus is U minus plus something. in U minus. So, sorry, the evaluation at U plus is evaluation at U minus plus some tau. So that's what a deformed disk looks like. And we examine what happens when we let tau go to infinity. So from this picture, it's clear that this index 2 disk is rigid and the sphere can move, and the sphere, as tau goes to infinity, will go and hit that divisor. And then what happens is that when you hit the divisor, you form a bubble in the neck piece. Okay? And this neck piece has a C star action on it. So as promised earlier, we have a higher symmetry group. So now if you just look at the space of these disks times the space of these spheres, it's going to be two-dimensional, but we are going to mod it out by the C star action. And on the other side here is the tropical graph associated to this. So normally in a tropical graph, the intersection multiplicity tells you the slope of this E. But now, since we are dropping the intersection condition, sorry, the matching condition, we simultaneously also drop the slope condition. And the slope is allowed to be anything for the deformed edge. So now this V minus is allowed to move in a one-dimensional line, and that corresponds to the C star freedom here. So again, this freedom in the tropical graph corresponds to tropical symmetry. Do I have 5 minutes?
Yes.
Okay, thanks. Okay, so what I want to take out of here is I want to look at the possible set of discrepancies of the tropical weight across E. So normally in a broken map, this quantity is 0 because the difference of the tropical weights is a multiple of the intersection, is a multiple of the intersection multiplicities. But now since we are allowing this to move, this quantity no longer vanishes. And so we can look at the set of values that it can take. And in our case, this set of values is this semi-infinite line segment, which is a one-dimensional cone, which contains this direction of approach here, which is also this right side pointing arrow. Okay, so this is kind of important because when you fix this direction of approach, you don't, for example, want to count split disks where this U minus goes to the right side. So those don't get counted in this moduli space. So if you fix this left side, you only count the left side ones in order to get the homotopy equivalence. So that's where this direction of approach becomes important. Okay, so now I'm in a slightly better position to give a more rigorous definition of a split disk. So given a direction of approach, a split disk is a version of broken map with no matching condition on certain edges, and for which the set of discrepancies of tropical weights across E is the top dimensional cone containing the direction of approach. So eta is the direction of approach. So the set of discrepancies is a top dimensional cone containing eta. And let me point out here that it's important, this top dimensional cone is important because that's what will give us the full tropical symmetry required that we said we should get earlier in order that the orbit space is index 0. So yeah, this is a remark I've been making earlier. For broken maps, this quantity is always 0. And yeah, if we, for a fixed direction of approach and an area bound, there is a finite number of tropical graphs that exist. So the moduli space of split maps is given by counting the maps modeled on each of those different tropical graphs. Okay, so there's another example here. yeah. As before, this is also a two-dimensional example, but I put in this example to show that we can also have bubbling in the limit. Bubbling as in, I called the earlier one also bubbling, although new components didn't form, but we can also have new components forming. So in this case, we deform an edge with slope 1, 1 in this direction. So by that, so there are only two options because R square mod 1, 1 is one dimensional. So I'm choosing the upper diagonal option. And this is an example of a split tropical graph that you can get. So here there is new components formed. And this is another example. So the new component can form on either side. So, but there will be exactly one new component forming. Otherwise, you might have too much tropical symmetry. Yes. Okay, and in both cases, if you see, they are kind of, this edge is, in both cases, it is bending upward from the 1, 1 angle. So there's 1, 1 and it's bending upward. So that is to make sure that this direction of deformation lies in that cone. So here also you would notice that these two are roughly bending in the same side. Okay. So making it more complicated, moving on to 3 dimensions. So now the cones we are talking about are no longer one dimensional. We are talking about 2-dimensional cones because this is going to be 3 dimensions modded out by one of the directions. So suppose we deform maps which are modeled on the graph gamma, and we carry out the deformation in the direction 2, 1, 0. So I claim that this is a possible limit tropical graph that you can get. And the reason I think this is a possible tropical graph is because the direction of approach is always contained in the cone of discrepancy. So since I deformed in the direction 2, 1, 0, the discrepancy here contains the 2, 1, 0 ray. So this is a possible graph that I can get. But the problem is this: to get a full dimensional cone, I want a 2-dimensional cone, whereas, so this is just a 1-dimensional cone. So as you see, so V plus, so I can lengthen this edge without breaking anything. So that gives me exactly a 1-dimensional freedom, which is not enough. So to get around this issue, we take the direction of approach to be generic. By that I mean, instead of taking 2, 1, 0, I take an irrational 1, 0, which is a generic vector. And when I do that, in order to, this is one of the possible graphs. So if I take that irrational one, there is no way I can just have one bubble in the limit. So I need to have at least 2. And when I have these 2 different bubbles, that gives me 2 directions of freedom. So the discrepancy cone is of this form. So I have 2 parameters, T1 and T2, coming from the lengthening of the edge connecting to V minus and the edge connecting to V plus. And that gives me a top dimensional cone. Okay, and that's my last slide. I use this tropical Fukaya algebra to prove unobstructedness in the case where one of the pieces is toric variety and the Lagrangian is toric. So I'll stop here and I'll take questions.
Thank you. Are there any, let's wait for the clapping. Are there any questions for Sushmita? It looks like Hiro has a question. So Hiro, why don't you ask your question?
So I have 3 questions. That's a lot, so please feel free to,
Yeah.
you know, devote
I think
time.
maybe ask one and then
Yes.
we can.
Sounds good. So I'll ask the one that I'm most interested in. So could you say more about the issues in understanding the higher dimensional moduli, like relating the split and the broken and the unbroken?
Okay, so so one of the things which immediately comes to my mind is that in the broken, for example, we always require the tropical symmetry group to be trivial because we are dealing with dimensions 0 and 1. As soon as you go to higher dimensions, you have to deal with the combinatorics of that tropical symmetry group, which we have not dealt with. So that is, and another more fundamental issue is that we are using the Seelenbach-Monge perturbations scheme, which is not good for higher dimensions. And okay, then that's a different issue. That's the perturbation scheme. So forgetting that, in the broken, that's the problem, that the tropical symmetry group need not be trivial and you need to deal with the combinatorics, which we have not. And in the split, it's again the same issue, that we need to examine the tropical symmetry group in a more nuanced way.
Is like a higher dimensional like equivalence, whether it be via cobordism or stratified homotopy equivalence, like is such a thing expected?
Yes, but we'll have to figure out the right relations to write down.
Wonderful.
And we'll have to get into understand this tropical symmetry group better.
Great, thank you.
Does anybody else have any questions?
Yes, I had a question. I was just writing it out, but maybe I'll ask it out loud if that's okay.
Go ahead.
Hi,
Go ahead, Shil.
Sushmita, thanks for your talk.
Yeah,
I
yeah.
just had a quick question to make sure I was understanding the process of splitting. Just in the view of matching conditions, in terms of the sort of alternate point of view you talked about in terms of matching leading order coefficients. Same multiplicities and matching leading order coefficients, is what's happening that you're just taking the leading order coefficients on one side and deforming it by some action?
Right. So you may think of that as the ratio of the leading order terms. For the broken map, the ratios are the same, but now the ratio gets multiplied by a deformation parameter.
Okay, thanks.
If there's not others, could I ask another one?
Yes, of course.
Okay. By the way, I've selfishly put just links to the statement into the Google form from earlier, just in case people missed it in the chat. But the question is, so I don't know anything about like counting holomorphic disks in iterated P1 bundles. Like, when you first related the broken disks to actual disks, relative to L inside of not fancy X, I was like, oh, that's great. We can actually do like local to global looking things. Is it actually easier to count disks in iterated P1 bundles, like the kinds of things you get in these symplectic cuts?
So if you actually looking at what actual counting we did, the only application we approved is unobstructedness, right? So, and here the disk part of it just lies in the toric variety. That is not the iterated P1 bundle that you are talking about.
Sure.
So we have not done that, A, but B, it's simplified because when we are talking about these P1 bundles, these are the 0 and infinity divisors. They are relative divisors, so we don't have to worry about curves sinking into those divisors.
I see. Thank you.
Any more questions? Okay, I would like to ask one last one, if that's okay. Have you thought about how your unobstructedness proof relates to the one of Fukaya Ota Ono?
No, I've not thought about it.
Mohammed, do you mean in the toric case?
I mean, in the toric case, yes.
Yeah, I mean, the principle's the same. I mean, because you put yourself in a situation where everything is invariant. The only cycle coming out of the evaluation map has to be a multiple of the fundamental one. But even I think Sushmita, you wrote out the toric case in the paper, right? And the proof is
The toric case in, sorry?
There is a proof of the unobstructedness in the toric case in the paper.
Yes, yes.
Yeah, and it's a somewhat different proof. It's not exactly the same as what Fukaya Ono did.
I'm only saying it because it looks like even in the toric case, maybe it gives a slightly different, slightly simpler approach because it doesn't use all the additional symmetry which they had to use.
I'm not sure I would call it simpler. I mean, we get the symmetry in a different way.
Okay. Okay, if there are no more questions, I think we should thank our speaker again.